In previous lecture, we have discussed Saha's theory of thermal ionization. Now today we will discuss its one of the most important applications. In forthcoming lectures, we will discuss actually all the applications of this theory. But in this lecture, I am just going to discuss one of the most important applications of Saha's theory of thermal ionization. The first application I would like to deal with is to calculate the percentage ionization of an element. Actually, to calculate the percentage ionization of an element by Saha's formula under varying conditions of temperature and pressure, we need a knowledge of heat ionization. You know, when an atom, that is a neutral atom, is heated, then it gets ionized when we supply at least the energy equal to ionization energy of the atom. So let us suppose M equal to a neutral atom, and when it is heated it gets ionized. This ionization is a reversible process and it is represented as M equal to M plus E minus U. Here you know that this U is actually ionization energy of neutral atom M. U is the ionization energy of M, and or you may say this is the energy released in the process of ionization. Now we know that this U is equal to E times Vi, and this E is actually electronic charge and its value is 1.6 into 10 to the power minus 19 coulomb times Vi. And what is this Vi? This Vi is called ionization potential of the atom. So this Vi equal to ionization potential, and this is measured in volt, and when you will measure it in volt, the ionization energy will be in electron volt. Now from Saha's formula, which we have derived in the previous lecture, we know what is Saha's formula. So according to Saha's formula, of Saha's formula of thermal ionization. Thermal ionization. We know that this is x square over 1 minus x square times P equal to 2 pi me over h square whole to the power 3 by 2 times kt to the power 5 by 2 Ge times Ga plus divided by Ga into e to the power minus u over RT. This is famous Saha's formula. And you know here x is actually the degree of ionization, or how much fraction of the atoms get ionized. This x measures it. To know the idea of ionization, let us consider a concrete example. We will take actually two examples to clarify it. In first example, let our neutral atom is of sodium atom. So M will be now Na. This is sodium atom. First of all, we will calculate the different values of these G's for calculation of X. And we know from spectroscopy, you have definitely studied in atomic and molecular physics that this length splitting factor or a statistical weight or G factor, you may say, this G is equal to what? This is measured by the formula 1 plus J times J plus 1 plus S times S plus 1 minus L times L plus 1 divided by 2 times J plus 1. This is the general formula to find the value of G. Now we will calculate for sodium atom and its ion, and for electron the values of G. So first of all, we would like to find the value of G for electron, that is Ge. You know, for free electron, S is equal to 1 over 2, L is equal to 0, and therefore what will be J? As L is 0, so J is equal to only L plus S, not L plus minus S. In general, J is equal to L plus minus S, but when L is 0, then J is only L plus S. And what will be this? This will be 0 plus 1 over 2, and this is 1 over 2. So we have calculated all the values of the different quantum numbers. S, that is a spin quantum number of electron, the total quantum number J, and its azimuthal quantum or orbital quantum number L. So now we will substitute all these values of J, L and S in equation B to find the value of G for electron. So for electron, G is written as Ge, and when you will substitute all these values in equation B, you will find that Ge is equal to 2. I have not simplified it. We can see easily this calculation that Ge, when we will substitute the different values of J, L and S in equation B, you will simply get Ge equal to this much. So for electron, the statistical weight factor is 2. Now we will find the value of G for the neutral sodium atom. So you know the electronic configuration. Of sodium atom, that is Na atom. You know sodium is an element of atomic number 11 and its configuration in ground state is 1s2, 2s2, 2p6 and 3s1. And the ground state or lowest state, ground state of sodium, ground state of Na is what? This is actually 2s half. This subscript half represents the value of J. So, therefore, for Na atom, the value of L is equal to 0 and J is equal to half. You know the quantum number S is always equal to half. So now when we will substitute all these values in the equation B which I have mentioned above, then you will find what will be the value of Ga. Just like for electron, all the quantum numbers are same. So for Na, we will also have Ga equal to 2. You know the symbol Ga represents the statistical weight of neutral atom. Now we will find the value of G for the sodium ion, that is Na plus. So electronic configuration we will write first of all for Na plus. Electronic configuration of Na plus is, when Na will be ionized, the valence electron 3s1 will be knocked out. So its electronic configuration will be what? This will be simply 1s2, 2s2 and 2p6. And so the lowest state of the Na plus ion will be what? That will be simply 1s0. The lowest, or you may say ground state of Na plus is, what will be this? This will be 1s0. And so you can say that this J is equal to 0, L is 0 and S is half. And when you will substitute all these values in the above equation for G, you will find that Ga plus will be equal to 1. So this Ga plus is equal to 1. So you can see that we have calculated the values of G for electron, for neutral sodium atom and for its ion. Now we will substitute all of these values in the Saha's formula. And remember one thing, that the ionization potential for sodium atom is 5.2 volt. So for Na atom, Vi is equal to 5.2 volt. So from A, I have mentioned the Sahaj formula in equation A, and now this A will be written as x square over 1 minus x square times P equal to 2 pi me over h square to the power 3 by 2 kt times 5 by 2. Here there is Ge times Ga plus divided by Ga. So put the values of these parameters. This will be 2 into 1 over 2 and e to the power, as u is equal to EVI. So let us put here EVI over RT. Say this is equation C. You can see that if we are given a particular value of pressure and temperature, then from this equation we can easily calculate the value of x. So at a given P and T, we calculate x from C. We can easily calculate from this. Now I would like to take another example to clarify your concept, and then actually the reason why I am taking another example is also that we will compare the degree of ionization of the two neutral atoms. So now we take an example of barium atom, ionization of barium. So let now the neutral atom M is Ba. Now we will calculate the different values of G, that is for Ba and Ba plus. So you know electronic configuration. Electronic configuration of Ba is what? This is 1s2, 2s2, 2p6, and you may write in this way, and the valence shell is 6s2, and its ground state is 1s0. Remember this, because this is a completely filled cell, and so J will be 0 here. Spins are actually cancelled, and so J is 0. And if J is 0 and the other quantum numbers are what? L is also 0, because the valence shell is valence electron is in S subshell, so L will be 0. So therefore we have J equal to 0, L equal to 0, and S has a fixed value, this is 1 over 2. So you can see from the above formula, by substituting all these values, for barium atom G will be equal to what? G will be equal to 1. So for neutral barium atom Ga is equal to 1. We have denoted the G by Ga for neutral atom, so I have written Ga equal to 1. Now when the barium atom get ionized, then we get Ba plus ion, and for this Ba plus, what will be the electronic configuration? Ba plus, for Va plus the electronic configuration will be 1s2, 2s2, 2p6, so on, 6s1, 6s1, and its lowest state or ground state is what? Lowest state is 2s half. So here you can see that again J is equal to 1 over 2, L is 0, and S is equal to 1 over 2. So if you will substitute all these values in the above formula, you will find that this Ga plus is equal to 2. And for free electron, I have already calculated the value of G previously. So here again, you know that Ge is equal to 2. Now, we will substitute the values of these different G's in the famous Saha formula to find the fraction of barium atoms that ionized. So let us say, let X dashed is equal to fraction of Ba atoms ionized. Then from Saha's formula, what we will write from Saha's formula? You can see easily that this will be x prime square over 1 minus x prime square times p, and this is equal to 2 pi me over h square to the power 3 by 2 kt to the power 5 by 2, and again here the factor is Ge times Ga plus over Ga, and we will substitute the values of different G. So this will be 2 into 2 over 1 and e to the power minus EVI over RT. And you know this Vi is now ionization potential of Ba atom. Ionization potential of Ba, and its value is also 5.2 volt. It means ionization potential of barium atom and that of the sodium atom are same. So I have written the symbol Vi for Pa atom too. So you can find this x prime from equation D if we are given P and T. So at a given P and T, we can calculate x prime from equation D. So you have learnt how the fraction of a neutral atom ionized can be found from the famous Saha formula. Now, from these two examples, we will just compare that in identical condition of pressure and temperature, how the degree of ionization of sodium is related to the degree of ionization of barium. We can relate these two degrees of ionization. So, in identical condition, you can see that this factor is actually the 4 times of the factor mentioned for sodium atom. You may see here that here is a factor 1, but except from this factor, all factors are same in RHS of equation C and D, and here is factor 1, and in place of it the factor in this equation D is 4. So you can see easily that in identical condition of P and T, that is for same pressure and temperature, it is clear from equation C and D that x prime square over 1 minus x prime square is equal to 4 times of x square over 1 minus x square. And we can compare from this result the degree of ionization of sodium atom and the barium atom. It is clear from this result that barium atoms are ionized more than sodium atoms. You may see here for different values of x. Now we will see some of the experimental value of x dashed. This is just a data obtained from the experiment. So you can compare from this table, just I am mentioning here. So see here, in tabular form I am just comparing the values of x and x prime. These data are experimental data which I have obtained from experiments. So here I am writing the values of x, and in this row we will write the value of x prime, that is corresponding value of x prime. So when x is found to be 20%, then it is seen that x prime is 38%, and when x is 33.3%, then x prime is almost 58%. When x is 50%, then the value of x prime is found to be 76%. And when x is 75%, then it is found, x dash is found 91%. So you can see from this table that the degree of ionization of barium atom is more than sodium atom if the condition of pressure and temperature are same. So I hope you have learnt how we can calculate the percentage ionization of a neutral atom by the famous Saha formula. In next lecture we will discuss its another important application, which is actually the explanation of stellar spectra. That was actually the main problem which Sahaj have to deal.